So yes, my apologies there for not being there for the handover.
Oh, no problem.
And
I think they gave me some.
you have that?
Oh, is this the? Okay.
That's the clicker. So yeah, Zach now is going to talk about adding Merkle-Mountain-Ranges and fly proofs to ETC. You know, this is something which there's been an ongoing kind of thread here. So Zach worked on BTC Relay, so has a long history of these kind of texts for linking chains together, and I am really quite fingers crossed that we have an opportunity to look at getting fly proofs into the next hard fork. If we can do that, that would be brilliant.
Thank you, Bob. Okay. Yeah, relay systems are not the only thing that would benefit from this, but they're definitely one of them. Okay, so I just want to say, like, from the beginning, right from the Bitcoin white paper, there was this idea, Section 8 right there, simplified payment verification. But I would argue that, like, this never really took off. People aren't using this stuff. And I want to ask the question, why? And I want to maybe answer that and come up with a solution to it. So first of all, the description of like how that works. So on Bitcoin there, they're just talking about transactions. But it could be any kind of data. And down here at the bottom row there, you would have the leaves of the tree, which are any kind of data. And in order to make a Merkle proof, you would the idea is that someone has just the root, and they don't have to keep track of all that data. So not everyone needs to run full nodes, and they would only need to take like a small little bit of that data in order to prove something against that root. But the problem is, how do we know that that root is legitimate? And this is the part that a lot of people forget to discuss when they discuss Merkle proofs. And this is unfortunately the really hard part to get right, which is that Merkle root is embedded in the hash chain. Okay, so you need to download all the headers in order to make sure that it's part of the legitimate chain. And that's a totally different kind of security, right? That's the proof of work chain. And then once you have that, you can have the Merkle root, and once you have the Merkle root and you trust that, then you can get these proofs from a full node. But the problem there is that this list in Bitcoin is really long, and in Ethereum, it's even worse. So just to kind of show how it works in Ethereum, it's a little bit different. There's a few of these trees. There's the transactions tree, the receipts tree, and the storage tree, or the accounts tree, which has storage trees in it. But it's the same idea. You have to prove something against a root, and then that root is contained inside another tree. But eventually, it comes down to a single hash that you have to trust in a block again. So see, they're all pointing back to the block at the top. And again, you have to have the entire chain in order to know if there's any validity to that. So let's look at the numbers. Just to get the actual Merkle inclusion proof part, that's super small, 400 bytes on Bitcoin and maybe 800 bytes on Ethereum, depending on exactly what you're looking at. But the real problem up here, again, is those headers. On Bitcoin, it's 50 megabytes. And on Ethereum and Ethereum Classic, it's 3 gigabytes. So this kind of blows up any possibility of using this in a way that we understand how to, the user experience that everyone's used to using the internet and just using computers. So if you have to download 3 gigabytes, that's going to take a while to do. And obviously, this is not good. So I just want to preface where we're going to get to, which is with Fly Client, we can get that down to 500 kilobytes. Okay, so that's, 3 orders of magnitude difference. At that point, you're not just talking about a speed up, you're talking about like entirely different kinds of software architectures that become possible. Okay, so I put this slide in here to kind of show like what's the typical UX now. This is Bread Wallet. I'm not really sure how to play the video. It doesn't really matter, but it just kind of shows that like this piece is loading when, because the way Bread Wallet works is it actually tries to make use of light client techniques, but it has to download the headers, and it says syncing, 59%, 60%, and the first time you install this app, it takes like 15 minutes. And then every time you open it, it takes 20 or 30 seconds. So I want to tell people to use it, but I can't because it's just going to confuse them, especially if they're new users. Okay, so with Fly Client, the first general concept is how can we do this without, how can we prove the work of the chain without downloading every single header? So the reason that you have to download every header now is because it's this linked list. And as we know in computer science, a linked list grows with the size of the list. So if you want to access one piece in the list, you have to run through the entire list. Whereas if we had a tree or something, this could be a lot better. But let's just take a look at an idea. What if instead of downloading all the headers, we just took a few random ones? Okay, we just asked for a few random ones, and you don't know the random ones that I'm going to ask for. So if you're able to return those, then maybe that means you have all the ones in between. But the problem here is without all the linkages, they're just floating in outer space. So there's no way to prove that someone didn't just create them afterwards, or there's no way to know what order they came in, or that they're part of anything really. So what we really need is a way to take those random headers that we ask for and link them together. So it becomes obvious that like some sort of tree would be useful here, but okay, we need to not, here's what I'm trying to show, is that we need to not only link the first header to these other headers, but we actually need to link the other headers to the ones before them, and the ones before them is kind of a recursive process. And the first kind of tree you could think of maybe using would be just a regular Merkle tree, which is what Bitcoin is using right now. The problem with that is that, so if you can imagine like A, B, C, D down there, those would be the headers, and you'd be adding them to this tree. Every time you add a new one, you actually have to change the parent hashes there. So if I were to add F, then I would have to change Y2 and Z1, which changes the root, the root of some of the other ones. So that becomes a problem when we're trying to link them together later, recursively like that. Okay, I don't think I'm ready for that slide yet. Okay, so this is where the Merkle-Mountain-Range data structure comes in. This was, at first, I guess, talked about from Peter Todd for a totally different use case. But you put the first item in, and that's really, right now, that's the whole tree, right? Okay, so this is the first block hash. Put the second one in, then you have to hash those together to make a parent. When the third one goes in, it kind of just stays on its own, and so you can see this structure start to form, where it's these, that's why they call it a Merkle-Mountain-Range. It doesn't necessarily only have one root, and as we add the next piece, you can see that sort of cascaded, and since BH3 was the same height as BH2, it created H of 2 and 3, and since that was the same height as its sibling over there, that created another parent. So as we go through this, maybe we can just kind of watch. I had block hash 6. Now we have 3 separate mountains. I had block hash 7, causes like the cascade to go all the way up. And what's nice about this is, unlike the Merkle tree I showed before, this one, you'll notice none of the parent hashes ever change. So when I add more leaves to it, there's no updating going on. There's just adding of new things. So that's a really important concept to this tree. And then here's a little bit more about how the tree is implemented in code. Like, basically, there's the tree representation, and each of these things has an index. And you can think of everything above the first row as just a sort of metadata, whereas the leaves of the tree are the real data. So if you want, let's say, leaf 8, there's an algorithmic process to go from leaf 8 to get up to index 15th item in the array, and that's the item that you know is containing leaf 8. Okay, so let's look at a proof. The way proofs work for this is, first, let's say if we want to prove leaf 8, which is node 15 there, we would first take all the peaks of the submountains. So we need all of those. And then we just need a regular Merkle proof from the local mountain that this item is in. So from 21 there down, that's the sort of the branch of that Merkle tree. So that would be a proof of 15, and it's also enough to prove 16, by the way, as well. And what's nice about these is when you send these to someone who's going to receive them and use them to verify, all you have to do is tell them that, like, that's node 14, this is node 21, and you give them like these node and hash pairs, and they can reassemble the whole thing into a tree on their side. And then they can verify by just making sure it has all the right nodes to index the one that you're claiming to have proven. So if we want to add 22 to this, it's really efficient. We're just going to add 2 more nodes, and that's enough to validate leaf 22 and 23. So we can do stuff where, like, maybe I request a proof for a few of the leaves, and then do some calculation. I'm like, oh, now we need a few more, so I can grab another proof for the next few after that, and we can keep track of everything really nicely. There's also an optimization where we can get rid of the implied leaves. Like, we don't need leaf 7, or we don't need node 17 there, because we have 15 and 16, and they can create that locally. Okay, so that's the bagging the peak process. I'm just showing here that, like, for the proof, for the root, since there's multiple peaks there, the way the root is defined is it's the concatenation of all the peaks and then the hash of that. All right, so how do we add this to Ethereum Classic? Well, this is how a header looks right now. There's all these items in it. We could just add an extra item at the bottom of it, and because this thing is RLP encoded, most of the surrounding software would have, like, very little to do to understand it. It wouldn't break that much because these things are already getting sort of decoded as lists. So it'd just be an extra item in there that, like, doesn't really affect anything else if you're ignoring it, and if you need it, you know where to find it. Okay, so how does the actual full fly proof work, though? Now, Benedict wrote the paper on this with a few other people, and he did a talk at, I think it was Scaling Bitcoin a year and a half ago. So there's a 30-minute talk there, and I think I linked to it at the end, so if you want to see, like, all the details, just check out the link at the end. But I'm just going to kind of just go over the main sort of themes behind it. So first, we pseudo-randomly request a sample of a few headers and proofs of their exact placement. Okay, then we request enough of these headers. If we get about 600 of them, then we have, like, a cryptographic level of certainty that they couldn't have just happened to have those exact 600. So it's enough to know that whatever we're proving from this, like, is legitimate and that work was actually done. And now, this is kind of a little bit maybe harder to realize why, but the way that the queries are done, instead of just picking 600 randomly, you pick them closer to the end of the chain, and that's to kind of intuitively, the reason for that is to protect against like a fork that someone would make where they're just using legitimate work from the early part of the chain and just forking off and making their own chain. So there's a whole like exact mathematical equation for like this probability distribution you're supposed to use. And then, okay, so then here's the really interesting part though. Instead of the person wanting to verify the information, instead of them just picking 600 random blocks, they actually can use the block hash for that randomness as like a seed to automatically pick the 600 blocks, because that makes the proof no longer tied to the people involved that are like requesting it. Now it's just sort of a bare proof. It's a non-interactive thing. And what's cool about that is like you could show it to anyone, anywhere, anytime. Like there's nothing else external to that proof that you would need to know to prove the entire work of the chain. So a lot of people might realize that usually using a block hash as randomness is insecure. But in this case, it's actually not, because so the problem with using block hashes as seeds is that if a miner, let's say they mine a block and they just happen to have this block hash, if they are somehow involved in the outcome of that randomness, they might just throw it away and make a new block. But in this case, we're just trying to prove how much work was done. So in order for them to create a new block with a new set of randomness, they actually have to do more work. So it kind of like cancels out that fact. So in the end, we have a single proof. It's about 500 kilobytes, and it proves the total work of the chain. It can be reused indefinitely to prove any other data in the blockchain, including historic data. So from that proof, you can make all these little Merkle proofs for like any piece of data that you want in the entire blockchain. Okay. So obviously the main benefit of this is that the user experience can be a lot better. We don't have to really download anything as like this ongoing daemon or process on the user's computer. They can literally just ask the way they normally would make a web request, get one piece of information and get it back. If we're using a peer-to-peer protocol, it's really awesome for that. But even if if our users are using like Infura or like some kind of centralized service, we can actually verify that information now. So sure, it's still centralized. It still has the problems of, the service can go down and that kind of thing. But we're no longer trusting a central party for what the information is. So I would say that alone is a huge benefit. Now, the other potential benefits, full node syncing, no longer requiring ugly checkpoints. Even Bitcoin, I was looking like in the docs for Bitcoin, even they have like checkpointing now. Because the problem is when your full node is trying to download the chain, there's no way to know if it's the legit chain until you get to the end. By that time, you've already downloaded like megabytes and megabytes, and you've just wasted a bunch of time. So this kind of gets rid of any need for that. It's just a one-time, I make a request, you send something back. If it's legitimate, I'll know it. If it's not, I'll just kick you out of my network. Okay, so this is the trustless ETC-ETH bridge thing. I think there could be some really huge potential there. Like right now to do these bridges, so Bitcoin Relay is probably the best example of a bridge like this. You have to relay all these headers. So all the Bitcoin headers are going into a smart contract on Ethereum. And it's expensive. They need to incentivize it. It's not properly incentivized. That's one of the problems with BTC Relay. But even if it was, it's hard to do that. Even if it was, it's a lot of data. It's expensive. And this, instead of trying to figure out the incentive structure, this eliminates any incentive. You don't need any incentive because you don't need to relay those headers anymore. So now if someone wants to make a proof for something that happened on the Ethereum Classic chain, and then have some smart contract on Ethereum do something in return, you can actually make that proof as like a one-time transaction. So whoever's trying to make that proof would relay the header themselves, because they don't need to relay all the headers now. They just need to relay the headers they're interested in. And some important things for the EVM. So once we have this Merkle-Mountain-Range structure inside, we'll be able to access any historical block hash, right? Because you'll just show, in a smart contract, you can show a proof to an earlier historic block hash that's part of like the chain that you're on. And then from that, you make a Merkle proof. So really, you can work with historic data of a smart contract inside of a smart contract. And a lot of things get just way cheaper and much more feasible in the way that these things work. I didn't put anything about Internet of Things up there, but I think this could be really useful for stuff like that. Like, I think there's a lot of potential for like really like low-level devices to be able to talk to each other, verify information, and create a network that's actually robust, because they don't need to send each other as much data, they don't need to trust each other, and they don't, there's not as much anyone can do to take down another node. All right, so now I'm going to get to the issue, which is the hashing algorithm that we have currently on Ethereum Classic and on Ethereum. The verification for that is extremely expensive. Inside a smart contract, it would be hundreds of millions of gas just to do one of them. On a computer, like on a phone, it's 20 seconds. On a laptop, it could be 10 seconds. And that's because like there's this process, you need this DAG structure, which is expensive to create. You could also send the person the DAG structure, but it's 16 megabytes, and it's growing exponentially. So I kind of question whether or not we want to continue supporting Ethash. Obviously, that's a really big change, and it's not something like I don't think anyone is solely in charge of. This is something we have to decide, like all of us. But right now, it doesn't. It's not ASIC resistance anymore. So that was like the main purpose of Ethash. There's a lot of good alternatives out there, and I think Alex is going to give a presentation at some point on switching to KCAC 256, which I think is as good of an idea as any. But that would actually make it extremely efficient to do, and that would make the bridges possible as well right off the bat, because Ethereum already supports like a KCAC opcode, so all that stuff would work natively. Okay, so just here's some links, and if you want to contact me or if you want to look at any of the other slides, that's my presentation. Should I take questions, or?
Absolutely.
Okay, does anyone have any questions? Sure.
If you get any requests for, I guess, other EIPs to make this easier for you, I guess what are they? And I also want to know, are there any particular algorithms that make this easier? So I know, Blake 2, I know it's going into this symbol. Does that help you at all? Or
I don't think that helps unless that's somehow used. We switch to that hashing algorithm instead of KCAC. But I would have to think about it. I mean, I definitely might have some ideas, but I'd have to think about it a little more.
Okay.
In terms of Vitalik's, kind of request of saying, talking about the data storage layer piece, and saying that if ETC had Fly client plus gas repricing on call data, so that is part of Istanbul as well. If we can have that gas repricing on ETC, but with the version, trick so that you're not backwards incompatibility doing, I think we could get to that position very soon.
Well, yeah, of course.
Sure.
I guess I just want to know if there's like a wish list of EIPs that would make for Fly client work on ETH. If you send that to me, maybe we can get a few of those
I see.
done.
Potentially getting it on Ethereum, getting this
yeah,
running
yeah.
on Ethereum.
Well, I mean,
okay, cool.
I presume you want both. I mean, okay. And actually,
I hadn't thought about it much just because up until a couple days ago, it seemed pretty clear that ProgPow was happening and then proof of stake. But yeah, happy to talk about that.
Okay. All right. Well, hooray.
Right, I think I solved that.
Yeah.
Last year, IOHK presented Nipple Pals, and this year you presented the Fly client. Do they do the same function? Are they complementary? Would they live together, or only one?
So I was really interested in Nipple Pals first. That's kind of how I got into this research. I was researching that stuff, see how that was working, and then this came out. And to me, this just blows all that away because. Basically, the amount of the type of cryptographic security you get with this is better. With that, there was it was focusing on these super blocks and the ability to kind of use a single block as a point. But yeah, there was just a ton of problems with those, and this is a much more, I think, elegant solution. So I mean, yeah, that got us pretty far. But this is overall. I think on every metric, just better.
Could both live in the same blockchain and some users or clients use one and others, or only one has to live into it?
I don't think so. This is kind of something that, well, there's ways to do a soft fork or a velvet fork to make this stuff work, but the big problem still is eth-hash, so there's not really a way to do a soft fork for fixing that.
And I think this is actually a fantastic opportunity to bring IOHK back into the ETC ecosystem as saying, you love that kind of stuff, don't you? Can you help with Fly client? Because we could really use with help on the research side and implementation of this into various clients.
Yeah, definitely.
This is absolutely in their ballpark. It's Charles's bag.
As far as I know, I'm the only one working on this right now. So if anyone is interested in helping out, just contact me. My email is up there. It's just my name, 23@gmail.
And I'd heard as well on the Ethereum research side, it's essentially only Vitalik that's looking at it. So it isn't there's anyone sitting and waiting. Really, yourself and IOHK are probably the best people in the world to do this.
Yeah, and I think it's starting to pick up more momentum too, because I just saw Zuko retweet last night that they're going to try and add that to Zcash. And Grin and Beam have added, are supposedly adding this too. So I think a lot of people are realizing that this is just a huge improvement in a lot of ways. One more question?
Sure.
Here.
Hi, Zach. Nice to actually meet you in person.
Hey, man.
So I had a question. Are there any trade-offs for using Fly client versus fully validating the node? And if so, kind of what are they and how do they work?
Yeah, it's always beneficial to run a full node over any of this light client type stuff. It's hard to say what exactly the benefits are, but with this you're relying on sort of the honest miner assumption. You're relying on the idea that more than 51% of the people mining this blockchain are doing it honestly. So you could have the longest chain, but if the transactions that make up that chain aren't valid, then the data is not really legitimate. And especially in this room, we should know that sometimes transactions can happen that are not necessarily deemed legitimate by everyone. And the only way to find that is with a full node.
Yeah. So that was basically my question. Just to restate what you were saying, it sounds kind of as if Fly clients are good if you have a light client need where maybe on my cell phone or something, I'm not going to be able to run a full node ever, but aren't exactly the thing for everybody used in all cases. And I guess I wonder then too, how do say ETH and ETC are communicating via Fly client, how do they resolve that if one day ETC or ETH change the rules and go with a different rule set, how do you resolve forks then if Ethereum is now talking to potentially 2 ETC fork chains? How does that work?
Well, mostly these light clients are just following the proof of work chain. So the same way that BTC Relay is now is if there's a chain that overtakes the longest chain, whether you consider that the legit one or not, that's the one that the contract will be following. So the same thing would happen with a bridge between Ethereum and Ethereum Classic. But it's important to emphasize that this doesn't affect anything outside of that. So even if that bridge got messed up, it would have no effect on Ethereum Classic as a network by itself. It would just have an effect on the bridge and maybe the health of that system.
Okay.
All
Thank
right.
you.
Thanks. Oh, all right. Just unplug this.
Now, where is Brooke? Oh, hello. Sure.
Okay.